Alrighty. Okay, now we are going to do a little review on use substitution. Probably the most important integration technique that you have in integral calculus, at least for first year. Um, some more powerful theorems and results come out later, like Calc 3, especially Calc 4, vector calculus. But that's for another year, maybe another student. um, so, um, use substitution is how we change an integral uh, so that it is in an elementary form, so that we can know what it should equal, I guess. So, like for instance, you uh, may know that the antiderivative, or the if I integrate x to the n with respect to x, and understand that the n is just some constant, or at least unrelated to x, that this is just like a power rule application, or like reverse power, that like we know the derivative of x to the n would look like n x to the n minus 1, uh, meaning that if I were to integrate this equation with respect to x, that undoes the derivative, the differentiation, without being too technical, and I get like x to the n plus some constant, I suppose, equals the integral of n x to the n minus 1 dx, let's say, right? That's then gives us a formula for sort of like a power rule type thing. And now if I uh, take this and divide both sides by n, I would get like x to the n over n plus, well, c. You could maybe say c over n, but you might have seen before, um, when we have this constant multiplying, if you have this constant, this undefined constant multiplying some number, like n is, or being divided by some number, um, I if you don't know what c is, then you also don't know what c over n is. So we just let it sort of eat the n, because it's just simpler to write c for something I don't know. And we would get the integral of x to the n minus 1 is this. And if I do a resubstitution here and say, oh, let's say m is n minus 1, so n is equal to m plus 1, then this tells me the integral of x to the m dx is x to the m plus 1 over m plus 1 plus c. Uh, and so this is our sort of reverse power rule. 1 on m plus 1 times x to the m plus 1 plus c is the result of that. Now, that's all well and good, and correct. Uh, but if I um, if we have something that doesn't look exactly like this integral rule, uh, then we can't apply it. Kind of like how you need a chain rule in differential calculus, right? That if I okay, like the derivative of e to the x is e to the x, um, but if you have like e to the x square, you can't just say, oh, that derivative is also e to the x square. You have to do like a chain rule type thing, right? Yeah, we have to, that's a way, and there's a way to argue that we can make it look like e to the x by redefining, like, um, u is x square. So that looks like e to the u, but then you have to take the derivative of the u, of course. Similar idea with integrals, that I can't, if I have, let's say, the integral uh, of 4x plus 3 squared, let's say, I cannot just say that this is 1 on 3 4x plus 3 cubed, right? Plus a constant. I can't, that's incorrect. That's wrong. We cannot substitute into these like uh, integration or differentiation formulas, unlike a lot of other areas of math where you can substitute these. Um, if I were to do a substitution, not only does it change perhaps the x in here, but it changes the integrate the sort of variable term here that we're integrating with respect to. Not to get too technical, but this is part of the reason. Uh, and so u sub is a way to, actually, I want that still. Yeah. U sub is a way to make this look like the elementary derivative up here. And for instance, we would say, um, in this case, say like, let u be 4x plus 3. Then if you do like a related rates type thing, differentiate with respect to x on both sides, you could argue that you get to say like a du dx equals 4, right? Um, Although often you won't see it written like this, you'll see the result sort of given like this, like du is 4 dx, sort of like you do the derivative on both sides, sort of normally, and then add this du and the dx. You could in a hand wavy way argue it as multiplying what we had here by dx on both sides if you treat the du dx like a fraction, although it's not technically uh, correct to treat it like a fraction. It's just there are occasions where you can treat it like a fraction and you get the right result at least. But regardless, this lets me write dx in terms of du. I can divide both sides by 4, or multiply by 1/4 rather, let's say. Same thing. I just like to think about what do I need to multiply by instead of divide by. And now I can change my integral to be completely in terms of u. 4x plus 3 is u squared. Um, dx is 1 over 4 du. The 1 over 4 I could pull outside, and now it's because it's the constant multiple, and now it's the integral of u squared du. And so that integral of u squared, this now looks exactly like our integral rule that I have at the top, albeit the label of the variable is different. That's the only thing that's different, is that one has x, the other has u. But regardless, I can use it and say that the integral of u squared is 1 on 3 u cubed plus a constant. And so that's 1 on 12 u cubed plus a constant. Again, that we're saying that like I don't know c, so I don't know 1/4 times c, so I'll just keep writing it as c rather than 1/4 c. And ultimately, my answer here should be in terms of my original variable, so I need to put back the x using my substitution, right? We had said that u was 4x plus 3. And so we put that back. And that's our antiderivative, right? This is sort of the most base level use of u sub, where you make some association between a new variable and an old variable, the u and the x in this case, that enables you to write your integral as an elementary form and then be able to say what it is, and then back substitute to get an answer. Um, you could there oftentimes you could like kind of guess and check your way to what the antiderivative should be, but the U sub is a more sort of consistent way to make sure, albeit maybe a little slower. As you do it more often, you might get used to sort of what happens for various sort of simple forms, simple integrals. Um, but this is not all that U sub is. I just want to preface that it's not just U sub is not just saying like U equals something like some function of X. U sub is simply a relationship between the new and the old variable that you then use in your integral. Um, so you could have a U sub like this. I could have a U sub where I say X is some function of U uh, uh, if I want if I want sort of a certain piece to inside of a function, like if let's say if I had like square root of X, and maybe I understand the X is positive. Maybe I want like a squared term in here, so I get square root of like U squared to cancel to just U, maybe absolute U, depending on the context. Um, uh, 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 right? I can do a U sub in that way to sort of make that happen in the integral, as long as I can change the rest of the integral into U stuff, and actually make use of it later, right? Not all U subs you can do will necessarily be useful. Um, but you can have these kinds of subs. You can even have just like a function of X being equal to a function of U, uh, say like in that case, if I had like the square root of 3x minus 1, I might, if I want to do that same kind of business of seeing like a squared term under here, I might say like 3x minus 1 is u squared. So I have some like function of x equal to some function of u, and work with it from that perspective. This is also uh, a way to do a u sub. Now, actually, you know what? Let's do a little example like that, where let's say I do have like 3x minus 1, and I'm trying to calculate. Maybe I'm trying to calculate this, or often too, what teachers or what professors do is they start with sort of like an easier integral, and they do u subs to create harder integrals. So yeah, just as a demonstration, this won't really get us to an actual antiderivative, but it'll showcase this funnier way, I guess, of using u sub. So if I say let let u square be 3x minus 1. And you know what? Actually, let's do this too. Let's go wild. Let's say there's a 3x squared minus 1 in here. This really won't be a useful sub in this case. But again, this is just a demonstration of how we could even begin to try to go about using it. Yeah, let's try. So again, I'm going to take the derivative on the left, the sort of normal derivative, like what's the derivative of u squared with respect to u? It's 2u, and then add on that du. I'm going to take the derivative on the right with respect to x and get 9x, and then add the dx on. So that tells me dx is 2u on 9x du. And so I can replace in my integral the stuff under the square root and the stuff in the dx. I could say it's 2u over 9x dx. But this is, oh, sorry, not dx, du rather. But this is not a very useful substitution. In fact, I haven't even really completed the substitution yet. And some professors may not like that I even wrote this with still an X in here. Um, if you do a successful U sub, or at least a logical use sub, I guess, or something that you could even begin to use at all, you need to go entirely from the old variable to the new variable. None of the old variable can be hanging around. So I need to find a way to replace this x in my denominator. Um, I can use my substitution though to do that. If I add 1 on both sides and then divide by 3 and then do a square root. Okay, now do I want the plus or the minus, depending? I'm not going to get into sort of technical details here. Let's just say I want the positive root in this case for whatever reason. Then I have found a way to replace my x. And so I can do that. I could say this is 2u on 9 root of u squared plus 1 on 3 and du, right? And I get that. And again, this is, if you were trying to actually calculate the original integral, this is not a useful substitution. This is making it worse. But again, it's kind of like I've created a harder integral, and now I could give this integral as a problem, and uh, uh, a student would have to figure out how to use sub to get back to the original, um, and then how to go from there, perhaps. But this is an example of a sort of more extreme version of use substitution, where I have variables left over and I find a way using my substitution to replace them. Okay. Um, and then finally, I think we should talk just about what happens when you have definite integrals, right? So if I have 3 to say like 10 of uh, let's do like e to the 5 minus x. Yeah, let's just say that. Um, Again, the point here is that this almost looks like an elementary integral. It's like e to something. It's almost like e to a variable, but it's not quite. And so I'm going to do a substitution uh, to make this look like e to u, or e to a variable. I'm going to say u is 5 minus x. So du is minus dx. Um, and therefore, and because now I have a definite integral, the bounds should change. Although there's kind of two options, really. You either keep the bounds the same and you should write like x equals 3 and x equals 10 to really make it clear that you're not changing the bounds. And then later on, you're going to undo your substitution. So you have x's again, and then you'll evaluate with those x values. You can do that, or you can change the bounds into the u bounds. So we say like, if x is 3, then u is 2. And if x is 10, then u is uh, -5. Yes, right? So what was 3 turns into 2, and what was 10 turns into -5. And it doesn't matter that now we're going from a smaller number to a bigger number. It's not like we just like add a negative because it's going in the opposite direction or something. No, no, no. This is just what the bounds turned into. I could flip the bound. I could flip it to be like -5 on 2, and then stick a negative in front if I wanted to use that integral property. But let's not do that. And then I get e to the u times negative du. Oops. Which is negative. I factor out the negative now. Get this. This now is an elementary derivative. So I know what I know what this will come out to. It's just minus, well, the integral of e to the u is e to the u, because the derivative of e to the u is e to the u. So I have that as my antiderivative, and I evaluate that between 2 and -5. Notice here, because I changed to u bounds, I don't have to go back. I don't have to go back to x. I can just plug in these u bounds and get that this is -e to the -5 minus -e to the 2, or -e to the -5 plus e to the 2. Okay, and that's an example with u substitution on a definite integral. Okay, so again, this is just really a base level idea on how we use u sub. Sometimes we use it to get it sort of immediately into an elementary form where we all know the answer. Sometimes u sub is simply used to make the integral look better, or make it look closer to another form where we could use another integration technique for. It is a very versatile idea, and it's you have to sort of see the different ways and get practice with the different ways that you can use it. But that is good for today then. Okay.